Hello and welcome back to Historical Geology. Now I want to look at the transition from reptiles to birds. It's really the latest studies or the latest readings that I've been doing on Archaeopteryx, which is believed to be the first bird. Later, what these studies are finding is that Archaeopteryx was probably just a feathered dinosaur, not quite a bird yet, because the bill of Archaeopteryx has teeth, and we know that birds do not have teeth. Birds must have evolved a little bit later. When we're looking at reptiles, shelled, yolked eggs, well, birds have that as well. Again, very similar skeletal features, and we'll go through some of those points. The same jaw and skull attachment, however, I just mentioned how the bill is different on Archaeopteryx than it is on birds. And then we find many fossils, especially the coelosaurs, even T-Rex, more than likely had feathers. There's another similar bird that around the same time found in China in the last couple years, I think it was 2015 or 2016. And this fossil of Confuciusaurus is just like Archaeopteryx, but it lacked the teeth. And what's special about that is it resembles a bird more closely. And here is that fossil with the feathers on it. And then this is an artistic rendition. But again, you can see that this bird or this fossil, which is probably the first bird, has these claws on its feathers still, right? So it's on its way to being a bird, but it's some of the points we make to link especially the coelosaurs with birds is that they both have this furcula. And the furcula is a fused collarbone here. So both the dinosaurs, coelosaurs, and birds have this fused collarbone, right? So telltale bones shared between the birds and meat-eating dinosaurs, these coelosaurs, the fused collarbone, furcula, which is in green here. The red ankle bone, astragalus, so there's a red ankle bone there at which is the bottom of the shin bone, which is basically the tibia there. And then also there's four toes, three facing forward, one back, three facing forward, one back. And note that in the coelosaurs, fourth toe, the back-facing one, is smaller and does not touch the ground, but it does on birds, on modern birds. However, I just told you about the Chilean study of University of Chile, how they use the gene expression found in modern chickens to change that fibula to make it longer. But also there's another work where they actually made a dinosaur leg. They had a chicken grow a reduced fourth toe. So again, showing the connection between modern birds and the coelosaurs. Then when we look at mammals, remember we had the proterotherid, and then we went to the pelycosaurs and the therapsids, and what they shared in common that they were synapsids with the one hole behind the eye socket. These therapsids eventually led to cynodonts, which is a therapsid. Cynodonts were warm-blooded, they had mammary glands, so they nursed their young, they gave birth to live young, they had fur. The details are in the middle ear. And there's video I'll put after this one. It's only like a 4 or 5 minute video from the series called Your Inner Fish, which you can find on YouTube. I recommend you watching this. But Neil Shubin talks about how basically the jaw bones of reptiles, in this case the pelycosaur here, eventually became a therapsid, how for mammals that jawbone got much larger, and these ancillary secondary bones changed to become the stapes, incus, and malleus, which are the bones we use to amplify sound. And we have very acute sound, much better than reptiles, because these bones in the back jaw were transitioned into our inner ear bones. So that's kind of what links the mammals to the reptiles. So watch this video and you'll learn more about it there. But just learn that we're looking at the stapes, the incus, and the malleus. So I'll be asking questions about these mammals, right? So we have this cynodont ancestor, and you can see that multituberculates, which are pretty important. They went extinct in the Cenozoic, so we'll say more about these. They're some of the mammals that really were important during the Jurassic Cretaceous periods. And then you'll see that today we really have three groups of mammals: the monotremes, which are kind of like the platypus. These are still lay eggs, and so that kind of links us over to some sort of reptilian ancestor. The marsupials, and then the placentals. And finally, this chapter ends with the discussion of the mass extinction at the end of the Cretaceous that basically killed off everything that weighed pretty much more than about 10 to 12 pounds. And one thing that we find at the boundary between the older Cretaceous strata and the younger Paleogene strata, or the Cenozoic, is a layer that's enriched with this iridium. And iridium is a platinum group element, and iridium is not very common, or at least these platinum group metals are not common to crustal rocks. They may be common in cores of planets, like our core will have higher concentrations of these platinum group metals, but also meteorites have these. And so remember, meteorites consist of that trollite and chondrite. And remember, the chondrites are more rocky material, and the trollite is more of these iron meteorites. And that trollite or iron meteorites and the chondrites, what they represent planetesimals that got big enough that where they started to experience gravitational differentiation. The heavier metals, like the platinum group metals, iron, nickel, platinum, iridium, would sink to form the cores of those planetesimals, and lighter elements would form the mantle and crustal materials of these planetesimals. But eventually these planetesimals will crash into other planetesimals or other planets and just get shattered. So that differentiation event separated these elements, and now collision between other planetesimals makes a bunch of meteorites. So we get stony meteorites, the chondrites, and we get iron meteorites, the trollites. And so that's why we find some of these trollites or some of these asteroids are enriched in these iridium or platinum group elements. And we find this anomaly in many places around the world. One of the first places where it was found is in Gubbio, Italy, and it was work done by Walter Alvarez and his father over at UC Berkeley. And they actually wrote a book on this called T-Rex and the Crater of Doom, where they realized that an asteroid was probably what killed off the dinosaurs. For a number of years in the 80s and really into the early 1990s, they searched for the crater. And for years and years, the Petróleos Mexicanos, the Mexican-run petroleum company here, they were doing a bunch of surveys in the Gulf of Mexico, and they knew some anomaly existed here. And they finally shared their data. The crater is found down in this region here. But you can see in different places of the world, we find this anomaly where we see a spike or we see a higher concentration of iridium compared to what the value should be. So in fact, the data I'm going to show you is from New Zealand here. And here we're looking at that boundary layer clay which separates the older Cretaceous rock from the younger Paleogene or Cenozoic rock, right? So this is from Woodside Creek in New Zealand. And we're seeing that the concentration of iridium starts off relatively low values, but right when we get to the boundary layer, we get this spike or this increase. And then younger sediments in the Cretaceous Paleogene boundary show a decline in that. Another thing that you would expect, if there's a big asteroid that hits the planet, there must be a lot of dust and soot that gets thrown up into the atmosphere, and the concentration of soot or fine particulates in the sedimentary boundary layer, you can see really another spike in this one here between the Cretaceous and here it's called the tertiary, but we don't use the word tertiary anymore. We use the word Paleogene. But you can see there's also a spike in the concentration of soot going on there. So some of the features we're looking at, the significance of this iridium anomaly is that iridium is rare in crustal rocks, but is found in much higher concentrations in some meteorites. So I talked about those planetesimals and the exploding, crashing planets there. Some investigators propose a meteorite impact to explain the anomaly and further postulate that the meteorite, perhaps 10 kilometers in diameter, set in motion a chain of events leading to extinctions. In fact, there's a recent paper that suggests it was really a combination. In fact, this one just came out in February of 2019. A couple of papers that were published in Science, and so this is a kind of a summary out of Scientific America where they looked at both papers. Both papers agree that it was sort of a 1-2 punch, or two things were going on. One, there was these large eruptions of basalt lava in India, and called the Deccan traps. And again, just like the Siberian traps that cause the Great Dying, the end Permian mass extinction, this one was a similar long-lasting eruption which produced lots of volcanic gases and toxic chemicals and probably had some global warming effects. Maybe ocean circulation was changed to some degree in terms of that hydrothermal circulation. One group of researchers in these two articles, a group from UC Berkeley, believed that the impact was right around the timing of this extinction that caused these eruptions in India to accelerate and really perpetuate this change of climate and on Earth during this time, which killed off the dinosaurs. The other group from Princeton thinks that there were intervals of eruptions and the asteroid probably hit between one of these intervals. But nonetheless, it seemed like the dinosaurs were already on their way out. Their numbers, their species were being reduced, and then these eruptions and the impact, crazy coincidence in the geologic record, occurred, and it wiped out these dinosaurs. So going back to these bullet points here. So some Cretaceous Paleogene boundary sites also contain soot and shock metamorphosed quartz. That's another thing we see. Some of the minerals in the rock show a texture that can only be formed by an impact, and those are called tektites. And your book talks about tektites as well. So both of which are cited as additional evidence for the impact. About 60 times the mass of the meteorite was blasted from the crust high into the atmosphere, and the heat generated at impact started raging forest fires that added more particulate matter to the atmosphere. So that's the soot that's going up. Another thing that was interesting is that this impact site is believed to be the Chicxulub crater in the Yucatan Peninsula, and this area is underlain by lots of carbonate rock, and the carbonate rock has carbon dioxide. So imagine this impact probably vaporized all that limestone, all that carbonate rock, and just added a ton of CO2 into the atmosphere. So again, changing the climate, probably warming it to a great degree. And here's that KT boundary or KPG boundary again. Now, the other thing is sunlight was probably blocked for several months, temporarily blocking photosynthesis. So there was collapse of food chains, extinctions followed. And then with this greatly diminished sunlight, temperatures would have dropped drastically. Another consequence of the impact is that vaporized rock would have added sulfuric acid and nitric acid. So kind of what I was saying in terms of the added CO2, but also we're adding sulfuric acid and nitric acid into the atmosphere. So heavy acid rain, devastating the effects on vegetation and marine organisms. And then finally, Mesozoic extinctions have not been explained to everyone's satisfaction. So most people concede, yes, there was a meteorite impact. We have the evidence for that. Like I said in these recent studies that just came out in February, it seems like the volcanic eruptions in India, the Deccan Traps, and this meteorite impact was a 1-2 punch that really killed off the dinosaurs. The vast shallow seas that covered large parts of continents regressed by the end of the Cretaceous, and the mild equitable Mesozoic climates became harsher and more seasonal by the end of that area. So that aided in the extinction. Nevertheless, these extinctions were selective, and no single explanation accounts for all aspects of the crisis in life history. In the Yucatan, we also have these cenotes, which are these pools that make an arcuate pattern which outline the traces of that Chicxulub impact crater here in northern Mexico. So again, there are several lines of evidence for this impact and the demise of the dinosaurs, but it seems like volcanic eruptions, again, a culprit, but in this case it was accompanied by an asteroid impact. Well, that's all for now.